Hola, soy Franco.
Y yo soy Agustina. En este video vamos a hablar sobre la ley de los gases, en especial sobre la ecuación de estado para gases ideales.
Existe una relación simple entre el volumen de un gas, la presión, la temperatura y la cantidad de moléculas del gas. Esta es igual a P por B, que es igual a nRT, donde n es el número de moles y R la constante de gases ideales iguales a 8,03 joules sobre Kelvin mol, y T es la temperatura definida en grados Kelvin. Un mol tiene aproximadamente 6,022 por 10 a la 23 moléculas. Este valor es conocido como número de Avogadro. Dependiendo de la sustancia, vamos a tener diferentes masas, pero el número de moléculas y átomos no varía.
Ahora bien, veamos un ejemplo simple. Por ejemplo, si tomamos un mol de cualquier tipo de gas a presión atmosférica y a temperatura ambiente, y queremos saber qué volumen ocupará, vamos a utilizar la ecuación de estado de gases ideales. Despejando B, vamos a obtener que B es igual a nRT sobre P. Si reemplazamos con los valores que corresponden, vamos a obtener un volumen igual aproximadamente a 24 litros. Este resultado es independiente de si el gas se tratará de helio, de oxígeno, de nitrógeno o dióxido de carbono. Mientras se tenga un mol de gas a presión atmosférica y a temperatura ambiente, siempre se tendrá el mismo volumen de 24 litros.
Y a continuación, veremos una experiencia realizada por Walter Lewin sobre gases ideales.
So let's now bring the ideal gas law to a test. And the way I'm going to bring it to a test is as follows. I have here a volume, copper, there's air inside, and I'm going to heat that up. I'll make you a drawing on the blackboard. Here is that volume, and there's an extremely thin tube which has almost no volume, and at the end is a pressure gauge. So there's a pressure gauge here which gives us the pressure, and the pressure is given in pounds per square inch, much to my regret, but that's the way it is. For your recollection, 1 atmosphere is approximately 15 pounds per square inch. It is also a gauge that measures overpressure. In other words, if you expose it to 1 atmosphere, it will read 0. Just when you go to the gas station and you measure the pressure of your tires, that is also a gauge that measures overpressure, the difference between inside and outside. This has a valve here, and I can connect it with the outside world, and when I do that, then the pressure is very close to 1 atmosphere, regardless of what the temperature is here, because it's connected to the universe, so the pressure in here will then be 1 atmosphere. And that's the situation that we have now. This valve is open, and it is in melting ice. And so melting ice, T1, is 273 degrees Kelvin. P1 is 1 atmosphere, and V1 is some value that I don't know. I close this valve, thereby the number of moles of air in there is fixed. That's not going to change. So we have 1 atmosphere inside now, and whatever n is of no importance, but it's not going to change. Now I'm going to put it in boiling water, and so I know now that T2 will become 373 degrees Kelvin. I want to know now what P2 is, and the volume is hardly going to change at all. It changes because of the expansion coefficient of copper. And I made a small calculation based on this size, and it turns out that the extra volume that you get because of the heat is only 0.5% of the original volume. So we can forget the fact that V2 is just a hair larger than V1. It's close enough to say that these are the same. And of course, we have the same number of moles. So now we can predict with the gas law what the pressure is going to be when we stick it in the boiling water. So we're going to get that P1, V1, equals nR T1, P2, V2 equals nR T2. I divide these two equations, lose my N and my R. We agreed that the volume was the same. And so we find that P1 divided by P2, T1 divided by T2, or the pressure P2, which is our goal, equals the 1 atmosphere pressure, which is P1, times T2 divided by T1. And that is, T2 is 373, T1 is 273. So it is 1 atmosphere times 373 divided by 273. That's what the gas law predicts. And that ratio is 1.366. So P2 is then 1.366 times 1 atmosphere. Now this gauge is an overpressure gauge. So therefore, you're not going to see this number, but you're going to see the difference with 1 atmosphere. So what the gauge will show us is 0.366 times 1 atmosphere. And since it is calibrated in pounds per square inch, it is 0.366 times 15 pounds per square inch, and that is about something like 5.4 pounds per square inch. So that's what I predict, and we'll see how close we get. You're going to see this, if all works well, on, yeah, there it is. I'm going to set the light situation a little better for you. I can even make it a little darker. So you see here this gauge. And see, notice it is 0, even though it is in ice water. This valve is open, and so it is at 0 because it measures only overpressure. And now we're going to close this valve. The valve is now closed. And we're going to stick it. Here is this object. That is the volume. Looks like a bathroom floater to me in a toilet flush. That's what it is probably. And now it goes into boiling water. And now look at the pressure. There it goes. 3, 3.5, 4. That's overpressure in pounds per square inch. 4.5. Let's just give it a little bit more time. It will take a while, of course, because gas is a very good insulator, so it may take a while for that gas in the copper ball to, it's already close to 5. We don't have to wait, of course, for the thing to become all the way 5.5, 5.4. But it will probably go up if we wait. It's now 5. Not much sense in waiting. What I want you to realize, what happens, or I want to ask you actually, what happens if I open the valve now? Yeah? What happens? Yeah. So if I open the valve, then 1 atmosphere. Some of the high pressure stuff gets out, 1 atmosphere settles inside, and so since this one is a overpressure gauge, it will be 0. So right now, it's 5. That's fine with me. That's very close. That's within 8%. Previous class we had 5.3, but we were a little bit more patient. I will open the valve now and watch what happens. Goes back to 0. So some air was let out because the pressure of the air inside is higher, was higher than 1 atmosphere. So we've seen a test, a reasonable test, first application of the ideal gas law.